We're into Module 9 now, in the last half of Chapter 24. We'll start off looking at probability mass functions. These are something that we've actually considered already, but never with this new set of language that we now need to introduce. The probability mass function, or PMF, of a random variable x is the set of probability values that would be assigned to each of the possible values that x might have. Each of these values of the probability must individually be between 0 and 1, but might be 0 or 1. And when you sum them all up, those probabilities are lumps that when you sum them all together, they must sum to 1. The probability that the random variable takes some particular value, or the probability that your xi has one particular value, xi, is pi. So let's not make this overly complicated. When you roll a dice, the different values that x can take are 1, 2, 3, 4, 5, 6, and the probability pi is 1/6 for each. You sum them up and they're 1. So you're already familiar with something that would very easily be described as a probability mass function, but that's just one example. And now this in general, the PMF is what we're considering here. What is a probability mass function? If we plot it, it would be the probability lumps at each of the possible xi values for all range of x that you might have. So when you think of x, it might be what score you get when you roll a die. It could be 1, 2, 3, 4, 5, 6, and then the probability lump that you'd put in each of those would be 1/6. Here's another example, just to give a possibility. Suppose that x is the number of students who take quiz 2 in a class in which 5 students are enrolled. So yes, I used to teach courses on this topic to as few as 5 students, and this is a probability mass function that would tell me how many students that I might imagine is appropriate for telling me how many students might be there on some randomly chosen day when I give out quiz 2. And here you see that there may be 0 students there to take the exam, 1 student, 2 students, 3 students, 4 students, 5 students. And the most common possibility is that all 5 of the enrolled students are there, so that's where the probability mass function has the highest value of probability lump there, where it's 0.35% probability that on any randomly chosen day when I'm ready to give quiz 2, all 5 students are there, and smaller probability lumps on each of the other possible numbers of x. And there's a probability mass function that might be useful to describe that way. Next, we're going to introduce what's known as the cumulative distribution function, which your book, and I've never seen anyone else call it this, but your book calls it the distribution function. Because I'd like you to be more familiar with how others describe it, I will be using the term cumulative distribution function, CDF, for discrete value conditions like this number of students or the roll that you get with a dice, with the roll of a die. That is most often we're going to be using the PMF. When we get to continuous variables, it turns out the CDF is most valuable for those. But we can define the CDF for a random variable x, and it's just the probability that for any given value of x, we'll have a function that we'll call f of x that is going to tell us the probability that the variable can have that value or less. So that's why it's called cumulative, because it's that value or less. It doesn't sound particularly useful, but in fact it's extremely useful once you get to familiar with how to use it. In other words, the probability that the variable will have a value less than or equal to the value x. And the CDF is the plot of the sum of the lumps of probabilities from the smallest x to the particular x of interest at that point. Why we do this this way by nature. Once you've summed up all the x's, that capital F of x is going to climb from 0 up to 1, and it must reach 1 by the time you get to the end of all possible values of x. So for the same example problem that we had previously, where in the last example, you saw the number of students who took quiz 2 could be 0, 1, 2, 3, 4, or 5, and there was a probability lump associated with each of those. To calculate the corresponding CDF for that case, what we do is we need to add the lumps from left to right, and we never let this become a decreasing function. So we just add the lumps and keep adding until we get to 1 as we go to the right. So again, the probability that 3 or fewer students will take quiz 2 is 35%. The probability that more than 3 students will take the quiz 2, I can get as 1 minus 0.35. So 65% probability that 4 or 5 students will be taking the test, but we find the CDF most useful for continuous random variables, and this is what's known as a discrete random variable. So in this case with the PMF, and in this case we have a discrete variable. You either have 0 students, 1 student, 2 students, 3, 4, or 5 students. You can't have 4.5 students taking the quiz. So that's what makes this a discrete variable x in this case. So that's this example. For a continuous random variable, we'll look at variables that can take on any value within a given range. That might be the concentration of a contaminant, the strength of a sample, and we're going to have whatever units are associated for that particular variable. And with continuous random variables, things are definitely different. Now, we'll have different names for these things, and where the continuous distribution function wasn't particularly valuable in the last example, or it might have seemed a little awkward, now we're going to definitely need that cumulative distribution function.
For continuous random variables, we use a probability density function instead of a probability mass function. We no longer have lumps of probability. In order to define probability for a continuous variable, we always need to speak about an area, and to get area out of a function, we need to integrate. So some of the characteristics of a PDF, or probability density function, are that it must always be 0 or positively valued. It can't have any negative values. And when one integrates across the entire sample space, or the set space, all possible values of x, that is, the function must integrate to 1. In order to find the probability that a continuous random variable lies between 2 specific values, a and b, one must integrate from a to b. You no longer talk about, for continuous random variables, we no longer are so concerned about the probability of equality. One doesn't always, well, one wouldn't ask when considering this contaminated groundwater, what's the probability that the concentration of arsenic is exactly equal to 1 part per million? That's not of interest. But what you would want to know, what's the probability that the arsenic concentration exceeds some certain threshold, or is less than that threshold? So now we do care about probabilities across intervals, and not really concerned with equality. In fact, just forget about it for continuous random variables, and you won't be concerned about equality there. Whereas, remember, for discrete variables, as shown in red at the bottom, all our probability lumps had to be between 0 and 1, and when you summed all those lumps, you would get to 1, and we did have probabilities of equality only, because when you're dealing with whole numbers, you care about exact values. So, for example, on the dice, you would never ask what's the probability that the roll of the dice would be between 2 and 3. It was either going to be 3 or it was going to be 2. Can't be anything else in between. When looking at probability, then, we have to calculate this area. And as you know, that means we need to integrate the function between the points of interest in order to get our probability. Because of this challenge of always needing to integrate, we find the cumulative distribution function, or CDF, for a continuous random variable is more useful. It's defined as in the same manner as it was for a discrete variable, that is, capital F of x is the probability that x is less than or equal to x, and it can be calculated by integrating the PDF using the formula to get capital F of x. You integrate little f of x, and you integrate from minus infinity to the x of interest, and I just used y as the dummy variable for integration. Recall you've seen that before when you took Math 262. The dummy variable that we use for integration is just a choice. In order to understand the CDF better, please note that it's always going to be non-decreasing. It may have portions where it's flat, but it can never decrease. So it rises gradually from 0 to 1. It might have steps in it, but it always is increasing or at least staying the same. Notice that in this case, it asymptotically appears to approach capital F of x of 1. And it must get to 1 by the time all the state space or possible values of x have been considered.